My objective today is that you should come out of this talk having an understanding of how automated bug finding systems work. Our bug finding system deploys two approaches: symbolic execution and coverage-guided fuzzing. If you're not familiar with these approaches, we're going to take baby steps up to them. And there's sort of two running themes. There is, how do we lay out the system so that if a fancy new bug finding approach comes along, we can integrate it? And how can we kind of architect it all to work so that we can take independent bug finding systems and actually get them to cooperate, even if the systems weren't designed to cooperate in the first place? So before we get into this, let's have a bit of history. We created Cyberdyne for the DARPA Cyber Grand Challenge. This was a multi-year competition. There was 7 finalists. We weren't one of the finalists. However, Cyberdyne itself was the bug finding system in the team that placed 4th. The Cyber Grand Challenge, it is a capture the flag competition. This means that you have a number of competitors and they are given binary programs. They know nothing about these programs ahead of time. They have to discover bugs in these programs. They have to develop exploits for these bugs. And they also need to patch the programs so that they are invulnerable to these bugs. And the interesting thing about the DARPA Cyber Grand Challenge is that the competitors themselves are machines. There is no human intervention. They have to do this all automatically. And the way they score points is that they actually attack each other. When you develop an exploit, you attack a competitor. The attack works on their patched binaries. If your attack succeeds, you get points. If your patched binaries perform well, you get points. And so the competition itself, it really shaped the design of Cyberdyne. It had to be an automated system. It had to be able to find bugs on its own. It had to be robust against any type of program. We didn't know what type of programs we'd get ahead of time. Obviously, no human intervention. And one of the things that it actually had to do is scale. In the final event, we had a large cluster of computers available to us. And we wanted to make really maximize our usage of those computers. So let's go see how we laid out Cyberdyne. What does a bug finding system in general look like? Cyberdyne is the running example, and so I'll always tie it back to that, but I will also talk about more generic tools that are available. So our goal with creating a bug finding system is that it should actually find bugs. Otherwise, it's not a bug finding system, it's just a system. It should work on real programs. And most importantly, it should scale. And I have a few definitions for what I mean by scalability. First, it should scale to real programs, big programs. It shouldn't just get stuck trying to find bugs at the beginning of a program when really those bugs are somewhere deep in the execution. The other idea I have for scalability is that you should be able to take advantage of as many CPU resources as you are given. First, you should be able to take advantage of one computer. And I mean complete advantage of one computer. And once you can prove to me that you can use one computer effectively, then you can have 2 and more. And so we want to develop a system that can actually scale out to as many computers as you have available to you, and it should just work on big programs. So we're going to actually work up to what a bug finding system in the large looks like. We're going to start small, and in fact, we're going to start with a very simple fuzzing setup. If you're not familiar with fuzzing, then the idea is this. You have a program. It has been written in such a way that it is expecting good, valid input. It's not expecting arbitrary input, random input. And so it's possible that this program will just crash if you give it random input. But random input itself is usually not a very good way to find kind of deep bugs in a program, to find logic bugs in a program. And so ideally you want to give it mostly valid inputs, like inputs that get the program into sort of a deep program state, and then you give it something slightly unexpected. And so a simple way of going about doing this is with something called a mutation engine. It takes these realistic inputs or real inputs, and then it just starts, say, flipping bits or flipping bytes. It does a number of operations on those inputs, and the hope is that when you've sort of corrupted these valid inputs, something interesting is going to happen. And if you don't feel like creating a mutation engine on your own, there's some really, really great ones out there. Verdamza is one of them. We actually use it in Cyberdyne. ZZUF is another one. So this is sort of the process of a simple fuzzing campaign. We mutate inputs. This we can do as many mutations as we want, generate millions or billions of inputs. And we spend a bit of time doing this. We can execute those inputs. Hopefully, one of these inputs or more of them is going to cause a crash. We don't really know though. And luckily these two steps, they can be done concurrently. We can very easily scale the mutation execution. They're completely independent tasks. And so we're waiting. Hopefully bugs are going to fall out. That's the whole point of this fuzzing campaign. But what if bugs don't fall out? We've wasted our time, or we might have wasted our time. There's CPU resources. We have no way of really justifying our use. And the problem is that, this simple bug finding setup with fuzzing, there was no accountability. We didn't have a metric to show that our bug finding process was actually making progress. If you think of deploying a fuzzing campaign into the cloud, you should be able to justify at the end of the day that it has made progress, that you are potentially getting closer to finding a bug. And so the sort of most common way of measuring progress is to kind of ask yourself, has something new happened? Have we created a mutated input that has generated some new event that we can measure? And the sort of industry-wide and academia-wide approach to this is called code coverage. It's also, there's other ways of doing it like branch coverage. But the basic idea is we have produced an input that causes some line or some instruction of code to be executed that no other input has executed before. And this is great. We can now run our fuzzing campaign. We can measure code coverage. We can produce a fancy little graph that shows like, okay, we got code coverage, we got more code coverage, we got more code coverage. We've got this accountability, but eventually we're going to see decreasing marginal returns. The code coverage, it might just sort of top out and go flat. And then we're stuck twiddling our thumbs again like before. We're not showing progress. And so the most common way of getting around this problem is to use something called coverage-guided fuzzing. And so the idea with coverage-guided fuzzing is we say, okay, we've got this metric. This metric says that some input has caused a new event to happen. That must be an interesting input. So let's send it back around, send it back into the fuzzer, and tell the fuzzer to start mutating that input. And I think the best analogy for why this is a useful approach is hill climbing. We started with a seed input. We mutated it. It got new code coverage. It's kind of like we went up some steps. And now we want to go higher up on the mountain. And so we mutated it again, and hopefully we're going to build on the progress that we got based on the first mutation. And so this simple setup, we've got that original kind of pipeline. Take inputs, mutate them, execute them, hopefully crashes fall out, otherwise measure code coverage, send them back around. There is a great open source tool that already does this for you. It's called AFL. I believe that if possible, it should be integrated into sort of your daily testing system or your weekly testing system. It can be put into a continuous integration system. It is great. Try to use it. So in Cyberdyne, we've sort of taken this coverage-guided fuzzing layout, and we're just extending it. We've done a few things differently. For example, that small fuzzing pipeline, we've got a mini loop in there, and we do a lot of that stuff sort of inline in a single program. And we've tried to do it all in sort of a scalable way that we can kind of just run in parallel. So let's actually see how we took just this simple coverage-guided fuzzing architecture and started extending it. Let's sort of look under the skin of Cyberdyne. This is sort of our layout now. We've got the fuzzer. It's called GUR. This is an open source tool. You can find it on github.com/trailofbits/GUR, GRR. Not to be confused with Google Rapid Response. And what GUR does is it just takes inputs, mutates them, runs them, calculates code coverage, and it does this with really high throughput. It emulates all I/O in memory, and it can repeatedly spawn sort of emulated processes just over and over and over. It's able to skip lots of redundant setup code. Very easy to scale. You just run more GURs. The one thing it doesn't do is it doesn't do orchestration like AFL does. It is just sort of a cog in this larger machine. The next thing that we have is PySymemu. It is a binary symbolic executor. It is slightly harder to scale. Most symbolic executors are. I'm going to go into sort of the scalability challenges of symbolic executors later, but it's possible to do this. And this is it's a simple program. It's written in Python, and we will be releasing a variant of it in the first quarter of 2017. The last sort of tool that we integrated into the system is a completely third-party tool that came out of academia. It's called CLE. It's hard to use. There's never been a time where I felt like my investment into modifying it was worth it. But it can sometimes find bugs and hard to scale, and so I'm just not going to talk about it again. I can complain about it offline. And so the next system is what I call the Oracle. We have all these bug finding tools. They're independent. They're not really communicating with each other. They feed into basically your operating system, where you're just running the input on the program. Hopefully your crashing inputs will fall out. If they don't fall out, then you send the non-crashing inputs off to the Minset. And so this Minset is exactly that coverage measuring system before. And it is the key to cooperation, the key to making it possible for completely independent bug tools to actually work together. And we're going to see why this is later. So let's go down to a bit lower level into our system to start by looking at the Minset and how it's enabling collaboration. The Minset itself stands for the minimum set of inputs that produce the maximum amount of code coverage. And we want to minimize the set of inputs that produce code coverage because the fewer inputs you have to fuzz, to seed, to analyze, the more resources you can bring to bear per input. If you have a lot of computational resources, great. Maybe you want to have bigger sets of code coverage producing inputs. But sometimes, you're like me, you might only have your laptop and you want to run the system. The purpose of it, though, as we said before, is just to identify these interesting inputs. They get new code coverage, they're interesting, we send them back around. And so I'm going to show you the process of how the Minset works. We're going to start with just 4 inputs. Let's say they've come from the fuzzer. And so they were originally some nice program inputs, and we've mutated them. So we have the first input. It comes into the Minset. We try to measure it for code coverage. As the first input being measured, it's sort of setting the baseline of code coverage. So it's guaranteed entry into the Minset. And we can see by that sort of that red circle up there, that is sort of an image representing what the code coverage produced by the first input is. If we run the second input, it comes through, we measure it for coverage, and we compare that coverage to the first input. And we can see that we've got substantially more code coverage than the first input got us. When we ran the second input, a lot more code was executed. We touched a lot more, we got a lot more program state to be explored. And so we add it to the Minset. The third input, we run it, and it got more coverage than the first, but the total code coverage that we measured for the third input is subsumed by the first and the second inputs. And so we're actually going to kick that out of the Minset. We're just not going to include it. And this is something where it's adding stuff into the Minset. It's a heuristic, and so you run the risk of throwing interesting things out. But the idea is that hopefully eventually we're going to keep the most interesting things in. And then finally we get to the fourth input. It gets us new code coverage above and beyond all the others. It goes out that way. And this is great. We've taken 4 inputs and we've compressed them down into 3 inputs. But there's a few problems here. There can be redundancy in the Minset. And one of the sort of ways you can think about this is, over time, we're doing that sort of stair-stepping where we're trying to increase our coverage. We're trying to walk higher up this mountain. And so what if when we get up to, say, a certain height, a certain amount of code coverage, what if, all that coverage covered kind of something that an earlier case did? We saw that with input 2. It got a huge amount of code coverage. And it included the code coverage that input 1 got us. And so actually, input 1 is now redundant. But it's in our Minset. The other problem, again, with input 1 is it set the baseline of code coverage. We guaranteed entry into the Minset of the first input we tested. What if that input is just totally uninteresting? What if it just quickly exits the program? We have now sent this input back around our cycle. We're dedicating CPU resources to it. And it might not be getting us to any interesting state. It might be bringing us further from interesting program states. And so that is a problem. So the idea is actually, we've created this minimal set of inputs that have produced the maximum amount of code coverage. We need to compress it. We need to even make it smaller. We want to remove the redundancy. And the idea on doing this, I think the simplest way to do this is to sort of fold the Minset over on itself. Let's reconstruct it and do it sort of in a reverse order. There's other orders to do it, but reverse is simplest to see. So we had added inputs 1, 2, and 4 to the Minset. So let's flip them around. Let's start with input 4. We're going to run it through the program. We're going to measure its coverage. Because it's the first thing we're measuring, it's setting the baseline. And so I think a simple way of deciding that, just flipping it around is the right approach, is that the most recently produced input, input 4, is probably one of the ones that gets us the deepest in the program. So let's use that as our baseline. We run the second input. Again, it gets us a lot of code coverage. And so we're going to add it into this new folded Minset. That's great. And now we run the first input, that one that set the original baseline. It might have been very uninteresting. And it doesn't get us new code coverage when we compare it to 4 and 2. And so now we can kick it out. We've shrunk the size of our Minset, and now that gets us more resources, like fuzzing resources, mutation resources, that we can apply to this smaller set of inputs. There's a few things, though, that I've kind of shoved under the rug. Code coverage. I've said, let's just measure code coverage. It's great. How you measure this and what you measure is very important. And it can be really finicky, actually. You can have coarse-grained measurements and you can have fine-grained measurements. In my experience, a coarse-grained measurement like measuring basic blocks executed, measuring functions executed. These can be okay if what you want to find is shallow bugs. If the coarser grained the measurement you have, the smaller your min set's going to be, the more redundancy you discover. But if you have a small min set, you have more fuzzers per input in the min set. You have more static analysis, more symbolic execution. And so the more resources you have, it's just a brute force problem. More things are going to fall out. If you have a very fine-grained metric like branch coverage or the last n branches, then you're going to have a bigger min set. And this can be good and it can be bad. If you've got if you've got a big cluster available to you, then great. And sometimes, and this was the case in the DARPA Cyberdyne challenge, you don't know what program you're going to be operating on ahead of time. If you're doing like a code audit, you can start to tailor your coverage metric to that program, and that's usually a good idea. But in the case of the Cyberdyne challenge, we didn't know what programs we would get ahead of time. It's just whatever DARPA sends us. And so, there is no one-size-fits-all code coverage metric. Sometimes we want to measure one feature, like branch coverage. Another time, we might want to measure a different feature, like the depth of the call stack, or what call stacks we've seen. And in fact, maybe at the beginning, we want just a coarse grain measurement. We want to see if we can shake out these shallow bugs, because we just need to find an exploit, and maybe there's an exploit early on in the program. And so one way that you can go about this is that you can just measure all the things at once. And the more things you measure, the more fine-grained your metric becomes, the bigger your min sets, and the more resources you need. Another approach that you can do, and this is what we did in the Cyberdyne challenge, is that you can change how you measure coverage over time. If we want to start by measuring feature one, like branch coverage, we can do that for a little while. And then maybe we want to say, of those inputs that we have in our min set, which ones execute certain call stacks, which ones get us this other metric, maximize this other metric. And so that's where this folding process sort of comes in, and it's really nice. We can build one min set with one metric, fold it over with the other metric. And we can just sort of do this at regular intervals. It can be over the course of minutes, over the course of hours, or over the course of days. And so the nice thing to see here is that we had the min set as the sort of gatekeeper of what goes around to the other bug finding systems. And it really didn't care who was sending it inputs. It could be the fuzzer sending it inputs. It could be a symbolic executor sending it inputs. It doesn't care. And so there's no sort of collaboration problems with the min set. It's not actually finding bugs, it's just filtering out inputs. And so the real challenge with making a bug finding system that is automated is plugging in tools. If we suddenly there's a new open source tool that's great, it finds bugs, we want to be able to plug it in, even though it was never designed for our system. And so we need to find a way to integrate these things. The min set is sending good inputs around. How do we give those good inputs to other programs? The easiest is the fuzzer. So here's an example where we're going to see the symbolic executor. It's going to produce an input. It's going to go around. We're going to see it fuzzed. I'm going to talk more about symbolic execution later. But to start off with, we have an input. Those S's in the input represent symbols. The sort of simplest way to think of this is that that initial input with the S's, they really represent any possible input. That could be anything. And it is the symbolic executor that discovers a kind of instantiation of that file. It discovers that one of these sort of initial inputs can be this sort of blue input. And it can spit out lots and lots of inputs. It discovers lots of inputs. And so we see that this input goes through our system, we measure it for coverage, and let's just say it's added to our min set. And so we send it around. It goes into the fuzzer. The fuzzer is going to run its mutators. It's going to mutate them. And then we're going to see mutated inputs come out. We've got little squares on that representing the mutations. It passes through, goes into our Minset. This is great. We have now gotten collaboration. But collaborating with a fuzzer, it's trivial. Fuzzers, they don't care who sends them inputs. They don't care where their seed inputs come from. So integrating third-party fuzzers into your system, integrating third-party mutators, it's pretty trivial. But what if we want to send that input to a symbolic executor? Before we had that executor taking files that could represent anything, and now we're giving it a file that's only one thing. How do we make the symbolic executor work with some sort of arbitrary input? And I've said that integrating third-party tools can be challenging. And integrating symbolic executors in particular and making them cooperate is challenging. And the way we went about it is what I thought was the simplest approach. You just say, here's part of an input, the rest of it, do your normal thing. Treat it as symbolic. And this is very simplistic, but I'm going to try to convince you that this simple approach is the right approach, because symbolic executors themselves, they're not easy to work with. They're not simple programs. They are monolithic. They do a lot of things internally, and we want to fit them in. And in fact, they're not the easiest programs to scale. There's lots of scalability challenges in them. And so if we can integrate them in the simplest way possible, then we can kind of break through these scaling barriers. We can take a problem, in the case of symbolic execution, that is really, really hard, and we can sort of turn it into a trivially parallelizable problem. We can just run independent symbolic executors and make them work, and that's going to be our way of scaling them up. And so let's go learn about symbolic execution at a pretty high level and see where the scalability challenges are with it. And hopefully this will justify why our simplistic solution of sending in partial inputs is the easiest path to scalability. So symbolic executors, I said they take in these files full of S's, full of symbols. These initial inputs, these symbols, could represent anything. You don't know what they represent ahead of time. And so over time, the symbolic executor is going through the program. It's sort of emulating the execution of the program. And every time it comes to a branch, like an if-then-else branch, it says, OK, I want to explore both paths. Down the true path, the condition tested must be true. So let's log that condition. Let's assert that it must be true. And down the false path, let's just assert that it must be false. And so it's going to try to fork and explore. And I'm going to make a concrete example of this so that you can see. And I said that PySymemu, our symbolic executor, is a binary symbolic executor. It works on program binaries. And so this is sort of similar to just a real program. It's just a CPU emulator, a bit of a special one. It's got registers, it's got memory, and it operates on bytes, as well as on symbols and sort of these expressions of symbols. If we have two symbolic input bytes and we add them together, that is a symbolic expression. It's as an emulator, it's just got software implementations of every instruction or every practical instruction that most programs use. In the case of PySymemu, we've got implementations of most x86 and AMD 64 instructions. So let's see an actual concrete example. This is a picture from the great disassembler Binary Ninja. Check it out. It's usable and it's fast. And up there, this is actually its sort of intermediate representation for some x86 code. What we're seeing is we read in an input symbol. It could be anything. we're going to compare it against 10. And so what I want you to think about is, if you're familiar with the C language or Java or something, we have a switch statement. It's basically a whole bunch of if then else's. And we have 10 possible cases in this, or 9 possible cases in this switch statement. Case 0, do this. Case 1, do this, et cetera, all the way up to case 9. And so we want to say, okay, we've got this input, and it should match one of the cases. So we're going to compare it to the upper bound of 10. If it's greater than or equal to 10, we've got the false branch. We're just going to return from the function, it's an unhandled case. Otherwise, we're going to go down the false branch, and we are going to jump to the code that handles this case. So our input symbol is an index into a table that is telling us where the code is that handles the case. So let's see what the symbolic executor is going to do on this code. It's going to fork. It's going to say, okay, we've got this input symbol. We've stored it in EAX. We now do our conditional branch on EAX. Down the path here on your left, we see that the value is greater than or equal to 10. And so the possible values of that input symbol are anywhere from 10 to 2 to the power of 32, or 2 to the power of 31. All those positive numbers in that 32-bit range. And down the path on your right, we see that this is the case where we're going to handle our 10 possible indexes. But there's something a bit funny about this. We're actually handling negative numbers as well as our 0, 1, 2, up to 9. This is where we're saying, let's go handle one of the cases. And we see that the constraints are bringing in this sort of corner case that we didn't originally think about when we programmed this. And so again, the next step of the symbolic executor, fork. On that original path where we were out of bounds on the case, we just return, we don't care about it. That's like an early exit of our program. But down this other path, we now have to fork to handle all the cases and more. We can handle each of those 10 cases, but what about that big negative range? Where are we going to jump in our program? We don't know. That's undefined behavior. That is probably going to be a bug. And so what we can kind of see here is that we're going to fork a lot. How many possible places could that jump have gone? Not just 10. It could have gone to 2 to the power of 31 or number of cases. It can go anywhere. And so this is really the scalability challenge of symbolic execution. It is going to fork and fork and fork. You've got a bunch of branches, let's fork down them. If you've got a loop, every time around the loop, that's a fork. Branches and loops, this is going to really explode. And so the problem that you have with these symbolic executors is that it's hard to get them deep into a program. They're monolithic. They're doing all sorts of complicated stuff. And a lot of times they will implement different heuristics that the implementers hoped would get them deep in a program. One of those is like the symbolic executor could follow the forks that get them new coverage. But these are really just band-aids. You can throw a number of PhD students at this and they'll produce theses for their favorite metric, but it's not going to solve the fundamental problem. And in fact, I would say there is no solution or no generic solution to this problem. And so my idea is like, let's just skip over this problem. Let's sweep it under the rug. Let's pretend it doesn't exist. And let's find a way to sort of massage the symbolic executor to do what we want. And so that's where that initial picture got us. We said, let's just take an input. Let's chop off part of it, treat the rest as symbolic, send it into the symbolic executor. This is now a trivially parallelizable problem. We haven't solved the fundamental scalability problem of symbolic execution, but we have found a way to jump the symbolic executor deeper into the program. Maybe it's going to explore sort of shallowly there, but it's still deeper. It's still got access to more program state. This is an improvement. There's a number of different ways that we can, we've got new heuristics to choose where to jump in, but that's something that you can kind of tune to the program that you're analyzing. And so we're finally coming to the end, and we've seen the high-level architecture of Cyberdyne. We can see now the sort of communication around the system. We've got the symbolic executors. There's the initial one that's taking completely symbolic input, producing outputs. There's sort of these partial symbolic executors, and that's our approach to sort of massaging symbolic execution into a trivially parallelizable problem. And it's taking partial inputs, sending things out. These inputs, they're all going around, they're being fuzzed, and we've now got collaboration where there was none before. We've taken independent things, they're working together, and they don't even realize that they're working together. And this is the nice thing about this approach. So what we've seen is that we started with a very simple fuzzing campaign setup. We started with just taking seed inputs. We mutate them, we hope that crashes will fall out the other end. And then we observed that the problem was that we could just spend our whole lives waiting for those to find bugs, and we would never know if progress was being made. So we tried to find a way to sort of make these systems accountable. We tried to find a way of measuring progress, and we used sort of the industry standard code coverage metric. There's lots of ways of measuring code coverage. There's lots of different metrics that we can use, but we've now got a way of measuring progress. We integrated that into a kind of a higher level approach where we added this cycle, coverage guided fuzzing. And that gets us sort of more inputs. It's a system that's hopefully always pushing the boundaries. The Minset, the service that measures code coverage, it was the key to distilling a corpus. It was the key to deciding what we send around. And then we saw that we could start adding independent tools. The fuzzer, it collaborates with anyone. Then we had the symbolic executors, and we wanted to find a way to make those scale, even though fundamentally they're hard to scale. So we took the simplest approach. We just ran multiple symbolic executors. We turned a hard problem into a trivially parallelizable problem. And so now you've kind of seen how you can architect a bug finding system. It's simpler than you think. You can take AFL and you can add to it. You can make your own system and add AFL to it. When academia publishes their new fancy bug finding system, you just add it onto this, and you find a way to to take your inputs, send them in, add this collaboration. And so Cyberdyne finds bugs. Now you can too. I'm Peter Goodman. Thanks for listening to the talk.